Hi everybody. This is the third in our installment of videos going through the Thermodynamics and Chemistry 1 worksheet. This one talks about a bomb calorimeter, again, similar to problem 2, in this case with 1 gram of hydrazine in it. Hydrazine's got all kinds of industrial uses, but it's most often thought about as a rocket fuel. We're going to be burning 1 gram of hydrazine inside this bomb calorimeter. It contains 1,200 grams of water. And just like in problem 2, I have inserted that trailing decimal point because I think that's what they meant for significant figures. They tell us in the problem that the temperature increase was 3.5 degrees Celsius and that the calorimeter constant is 840 joules per degree. The problem actually asks us what is the Q, or the heat of combustion for 1 mole of sample. So we have to do a couple of things. We're going to calculate Q based on what we see here. And so that's per 1 gram. Right, and so we'll go ahead and we'll say Q of the reaction is, again, the opposite of Q of the water plus Q of the calorimeter, or the bomb. All right, so Q of the water, as before, is mass of the water times the specific heat of the water times its temperature change. And then we'll add to that the calorimeter constant times temperature change, just like we did before. All right, so negative. Mass of the water here, 1,200 grams. The specific heat of water, now we're going to be working in joules again, so this is that same 4.184 joules per gram degree Celsius, and times the temperature change, which was provided at 3.54 degrees. Giant plus sign so we don't lose it. 840 joules per degree times the same 3.54 degree temperature change. All right, and so our numbers then, when we go ahead and multiply 1,200 times 4.184 times 3.54, we're going to get the amount for our water, 17. I guess I didn't need to write this out, but I'm already in it, so let's do it. Okay, water, and then our calorimeter separately, I suppose, 2973.6. All right, add those together, and we get 20,747 and 232 thousandths. All right, joules. And that was Q of the reaction as it was done here. All right. Now, the problem didn't ask us how it was done here. The problem asked us how much per mole. So essentially what we're going to do, if we want to think about it this way, this number that we just calculated is joules, right? That's our unit right there. But it was per 1 mole, 1 gram, per 1 gram of sample, just because that happened to be what we started with. So what we know is that 1 gram of this stuff will produce 20,000 joules of energy. Now the way I would write this out is to say I want to start instead with 1 mole of hydrazine, convert that to grams of hydrazine, and then I know that 1 gram of the stuff liberates 20,747.232 joules of energy. Now all I need is the molar mass from the periodic table, so I go and I add up a couple of nitrogens and 4 hydrogens, I get 32,046. Sorry, that's a little cramped, 32,046 grams per mole. And so when I do the math now across, I've got my 20,747 number, I'm multiplying by my 32,046, and everything else is ones. So I'm going to end up with liberating 664,865 and some decimal stuff that frankly isn't going to matter, joules. Now that started with 1 mole of material, so I could technically write this as joules per mole, as long as you understand that the units, the way I've written this, the units are going to cancel so that all I have left is the joule. Since I started with 1 mole, I could technically say this is joules per mole. Okay. Significant figures, if I go back to the start, I've got 1.00 grams of the hydrazine, 3 significant figures there. I'm choosing to believe that they meant 1200 point grams for the mass of the water, so that'd be 4 significant figures. I got 3 for the temperature change, and the calorimeter constant, although it was expressed just as 840, typically if they're giving you a constant like that, you can consider it exact, so I wouldn't stress about that one. I'm going to round this to 3 significant figures to get negative 664. Oops, nope, sorry, 665. I can't read my own writing. That was 6648 right there. So 665,000 joules, or 665 kilojoules. And again, if you want to write it as kilojoules per mole in this case, that would be appropriate. But that's our answer. All right, so 2-step problem. We've got kind of the thermodynamics problem in black up there where we're going to figure out Q, and then essentially just a conversion factor where, again, I've used my Q data from the first part of the problem kind of as a conversion factor. All right, problem 4 comes in another video, so stay tuned.